All right, I'm going to do a couple sections in E&M today. We're going to look at, last time we looked at electromagnetic waves a little bit in a vacuum, some of the frequencies of it. Just a little review there. Electromagnetic waves can have wavelengths, gamma rays, which are really, really high energy, 10 to the negative 12th. In other words, an atom has, the length of an atom's, an angstrom, about 10 to the 10th, negative 10th meters wide. So you can have electromagnetic waves that oscillate up and down, 100 of them, in the length of an atom. That's 100 times they oscillate up and down as they travel at 3 times 10 to the 8th meters per second. They oscillate up and down 100 times. For it to be able to go in that short a distance, to oscillate up and down 100 times, would take a lot of push to make that happen. That push or oomph to make that happen is the energy. So gamma rays have such high energy. It's because if they have the ability to oscillate that fast, it takes a lot of energy to make that happen. They go all the way down, like radio frequency, AM waves on your car, they're 10 to the third, 10 to the, they're 1,000 meters long. If it takes 1,000 meters long, as it goes traveling, 186,000 miles per second, 3 times 10 to the 8th meters per second. If over 1,000 meters, 10 to the third, 10 to the fourth, 10 to the third, say 1,000, it goes up and goes back down. That's kind of slow compared to, the width of an atom, going oscillating up and down 100 times. So AM waves, that's amplitude modulation, AM type radio waves, which are those sort of frequencies, that's really slow. So do they have as much energy? No. That's why you can make AM waves, get blocked by things. They don't have a lot of energy, so you can block AM by gamma waves, gamma rays. So much goes straight through the earth. Why? Well, one of the reasons is they have so much energy, we can't absorb it all out. Things that it hits just oscillate with it or just let it, it just goes completely through it. We're going to talk a little bit about that today as electromagnetic waves in materials. Electromagnetic waves is just how often it oscillates up and down. That's in a certain amount of time. That's the frequency. The wavelength is the distance it takes for one oscillation. For visible light, say red light, red is about, say 600, we'll say 610 nanometers. In other words, the wavelength of red light is about 610. Green is about 520, 530, something like that, maybe 550. Green we see really good. So our eyes are tuned, our eyes to see it are detectors that are tuned so that if it sees the electromagnetic radiation oscillating, has a wavelength of about 500 nanometers, let's say, which is about 5,000 atoms long. Something that oscillates up and down one time, and that it's sensitive. It causes some change to happen. And that change, pushing electrons, gets collected by the, gets collected, goes to the optic nerve, goes to the brain, and our brain interprets it and makes the image that we see. Now, because the eye is just a detector. It's just like it's just like a camera. Can you do that for other wavelengths? Because our eyes don't see certain wavelengths very good. Yeah, you can have it for microwave. You can have a microwave camera, basically. You can do it for radio waves. You can do it for lots of things. It's harder to make it like a CCD camera, a two-dimensional camera array for like radio waves. The material properties are such as they are. And some of them with gamma rays, it's hard to even measure it because it just goes straight through stuff and you can't even see it. So how do you collect gamma waves? You have to actually, or especially ultraviolet, which gets close to gamma, high UV, you actually have to, you can't make lenses. You actually have to make waveguides, or basically it hits it at just an angle. You can't hit it at a high angle. It has to hit it just at grazing, just barely get into it. If it hits it at grazing, you can actually make effectively a lens that'll take a gamma ray and make it bounce off and focus it. It takes a lot of energy to hit here and go there, or to hit and go through. Gamma rays, some of the UV stuff, you can even make it easily have it go through and bend. So what you have to do, you have to hit it kind of at have it hit at an angle, and then and you have a bunch of, say, one here, one here, one here, one here, like here, 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 and here. And that gradually, over time, focuses it down to a point, or to what you're trying to get it to focus to. Properties of electromagnetic waves in materials. It's pretty deep science, and the engineering of it to make things we need requires material properties. Material scientists make good money if you can do it. I'm not a materials guy for it. Now, let's look at energy and momentum in electromagnetic waves first before we look at waves in materials. So 9.2.3. Energy and momentum in electromagnetic waves. Now, earlier they talked about in chapter 8, now we didn't do chapter 8 because of time considerations. They said that the energy, now I'll make this energy per unit volume. And so this is a ratio. It's basically the energy in a standard volume. How much energy you got in a standard bucket, we'll say. And that's equal to 1/2 epsilon naught the electric field squared, the magnitude of that field, plus 1 over mu naught and the B field squared. The magnitude of the magnetic field. And that's the energy in this volume of space. You just take what's the value of the electric field at a specific time, value that's in magnet, the value of the electric field at a certain time, value of the magnetic field at a certain time. Use those qualifiers in front of it and take 1/2 of it, energy per unit volume at a specific time. For a plane wave, for a monochromatic plane wave, which is what we discussed in the previous video, we said that B squared equals 1 over C squared, the magnetic field squared, and that C squared was equal to a mu naught epsilon naught E squared. So we could actually substitute here and put this in terms of electric field. So what we can do, if that's true, then that means the energy per unit volume for a monochromatic plane wave is 1/2 epsilon naught E squared plus mu naught epsilon naught over mu naught E squared, because we substituted this and this into there. Well, that cancels. E naught squared, E naught E squared, E naught E squared, that's 2. The 1/2 cancels, and we're left with just energy per unit volume for a monochromatic plane wave. For a monochromatic plane wave is just equal to epsilon naught E squared. But what is E? What's the electric field? The electric field, remember, we said that was equal to, for a plane wave as it's oscillating, that's just the magnitude of it, the amplitude, E naught squared, times cosine squared, kz minus omega t plus phi. And this is just the phase constant. In other words, if it didn't start at 0 degrees, it started at 20 degrees, started at 90, 180 degrees. What was it? Where did it start off in phase? Because for a wave, you need to know that. It tells you it's a different starting point. So that's interesting. So this is energy per unit volume. Okay. It's just a function of, it's just this. Okay. Now, also in the other chapter, now this is actually, you'll see this, and you may remember this in 212 if I got to it. It's in your 212 book. Something S, which is known as the pointing vector. I always thought it's interesting. The pointing vector is P-O-Y-N-T-I-N-G. It's named after a person, but it actually points in the direction of propagation of the wave. This S vector, this pointing vector, equals 1 over mu naught E cross B. And what is this pointing vector? It's the energy per unit time. Per unit area. Per unit area. Per energy divided by the energy per unit area over the time. In a certain amount of time, how much energy goes through a certain area. You can think of this as the energy flux density. Energy flux is how much energy goes through something in a certain time for this area of the plane wave. How dense that plane wave is. How much energy of a plane wave goes through a point in a certain amount of time. And that would be what the pointing vector tells you. Now, the book goes through a little bit more here. What I want to look at from this, we got B squared and E squared here. What's interesting from this, let's look at this term here. Let's look at this term here. And we can use the pointing vector as well. It works out. But the book does it in threes, and I'm going to go this route if you don't mind. Let's look at the average value of the energy density. The energy density. Let's look at that average value. And we'd say this average value, it would be like this. And they use a U, and I'll just say this energy density. I'll just write it out in words. We're going to find the average value of energy. Why average? Because it oscillates with time. It's going up a little bit, down with a little bit, up a little bit, down with a little bit. And at certain times, as it moves, that's going to be 0 there, or cosine of 0 is 1, but at say 90 degrees, it's going to be 0. Yeah. So it's going to be points where it goes to nothing. What would be the average value of this? Now, so I want to know what is the average value of cosine squared kz minus omega t plus phi. My answer is 1/2. You're like, Knight, come on. How is that a half? Now it's cosine squared, it's not cosine. Since it's cosine squared, what does that look like? If this is kz minus omega t plus phi, and that's the argument, and this over here would then be cosine squared kz minus omega t plus phi. What is that going to look like? Well, since it's squared, there's no negatives for the output. So it's all got to go like this. All going to be above that line. It's squared. Any negative ones or negative output for cosine becomes squared. So it's negative 1 times negative 1 or negative 0.7 times negative 0.7, 0.49. You get something like this. So it's got to be above 0. Now, how do I know it's a half? Well, I could do an analysis and average it all, look at all the points over time, and do all that stuff. Or we could get cute. And how could you get cute? Well, remember, cosine squared theta plus sine squared theta equals 1, right? We all agree to that? It's cosine theta over sine theta equals that radius, for the unit vector. Well, if something squared plus this one squared, these both have to be less than 1, and the average of cosine squared theta must equal the average of sine squared theta. Because cosine and sine are really just out of phase by 90 degrees. So the average value of them's got to be the same. They're just over time, or in this case over time as it would move out, as the argument gets bigger, it changes. But they're really the same thing because cosine of theta plus 90 degrees or theta minus 90 degrees is the sine of theta. So it's the same thing. So these have to be the same. And if these are the same, what's the only way for these two to be the same and equal 1? 1/2 plus that 1/2 equals 1. So cosine squared theta has got to be 1/2. So what I can say is the average energy density. So I can replace this term with 1/2 equals 1/2. Did I drop a C? Okay. Yeah. The average energy density is going to be, no, I didn't drop a C, epsilon naught E naught squared. Now, for the Poynting vector, you've got a 1 over mu naught. You've got to cross these terms. If you do that, you get something very, very similar for the average of the Poynting vector. 1/2 C epsilon naught E naught squared. Then they go to, don't worry about G for this. Now, why is this important? Because S is related to something. How much energy for a plane wave goes through a point at a certain time? You understand energy over an area hitting something over time. You understand that concept very well. How do you understand that concept very well? Magnifying glass. A magnifying glass. You take a magnifying glass. We'll just take something. Pretend it's a magnifying. Oh, is this? No. This will work. Happen to have this around. So here's your magnifying glass. We'll assume this is a circle. You'll take this magnifying glass. This is supposed to go off on that go-kart over there. And the energy goes through. It focuses it to a point, right? So all this energy that would go through this, it's a certain amount of energy. Here's the area. And then over time, it's how much, goes through it on average. But if you focus it on the magnifying glass to a point, you get that energy density really, really big. And if you focus it on your skin, and you focus on your skin, and it burns, and you say, ouch! And it burns you like that because it's hot. You feel that energy per unit time. You say, wow! When you focus it, that light's really intense. That light's really intense on me. That energy at this point, the energy density over time, is when light gets focused to a point and you feel it with a magnifying glass. That energy density. It's not just energy density, it's how much energy density you feel over a certain time. If the energy density was over, millisecond, you don't even feel it, right? But if it sits there and you let it glow, it'll get hot. It'll burn stuff. And, how can you start a fire with it or kill ants? You have to leave it on for a certain time because you got to convey enough energy to it. Energy density has to be high, but you got to have a lot of time on it as well. So that energy density per unit time, I got to make that light real intense. So I got to focus it to a point, we would say. So the energy density per unit time, we call that. Let's define that as I, where I is the intensity. And we'll say this is the time average of the Poynting vector, which is the energy density per unit time, how much energy you got in a certain area and how long it goes on it. That is, by definition, the Poynting vector. So the intensity of a wave, how hot it feels, that electromagnetic wave, how much energy is transmitted to you over a certain time. That's a constant. That's a constant. It's directly proportional to what? The magnitude of the electric field. You want to have more energy transmitted per unit time, more intense wave. Give me a bigger amplitude of that electric field vector. Which makes sense. The stronger the field, the more energy it's got, right? We see energy stored in fields. Now, they use a term called radiation pressure because if there's energy that's hitting it, I'm going to put this term, running out of space, I'm going to put it right down in here. Radiation pressure. They say radiation pressure, and they go through and define it, is basically the intensity of the light over C. Well, if light's hitting it, we say it's putting some pressure on it. It's pushing on it, right? That radiation pressure. It's a average force per unit area. So light's putting pressure on it. So if light's putting pressure on something, when it hits it, it could put a force on it. It can move it, want to push on it, right? What is radiation pressure an application of? Solar cells. You can make a cell for the sun. You can make a cell for wind, and it does a good job here on the earth. But you can use a cell for photons as well. SAIL, cell for photons. For electromagnetic waves, photons is just that's a particle analog of an electromagnetic wave. Because light's not a particle or a wave. We say that's more for later. But this average force per unit area, this push by electromagnetic waves, the sun pushes on things. And it keeps pushing, just like a cell. The problem is, in space, there's not a lot of radiation pressure because, we're 93 million miles away from the sun. Energy falls off as 1 over the radius squared. Because of the sphere gets bigger and bigger and bigger, surface area of a sphere is 4 pi r squared. So if it gets bigger and bigger, it falls off as 1 over r squared. But it's there. So to make a cell work, you basically need a big giant cell. 1/4 mile wide for a little small cellular CubeSat thing. To really make it push it. And it works. But how do you make that? We're still trying to figure some of that stuff out. Good thing is, it would still work. You keep on going all the way out to the outer planets. It would still work. Average force per unit. Now, that makes you think. You tell me, hey, Knight, if it's got pressure and it's force equals mass times acceleration, light should have mass. And I'm like, no, we don't think so pretty much. We haven't done an experiment to prove it. Now, I've talked a little bit more about this. The book talks about the observation, Basically, we don't think light has mass. Let's just say that. I'm going to erase the board here in a minute. Real quickly on this. This concept, as I erase the board, I'll just go ahead and erase it now and start on electromagnetic waves and matter next. But it makes sense that, if there's radiation pressure, light should have some sort of mass or be able to calculate a mass. And to show it does have a mass, we would think. It makes sense that it should. Well, we had a guy, when I was at UNC Charlotte, I was in grad school there from, just say in the 90s. I won't tell you how old I am. And he came from Cornell, I think, if I remember correctly. Professor did. And he said, he wrote a book that said light had mass. It was like a third order effect. Hard to see, but if you did the right experiment, you could see it. And we had a guy at Charlotte named Faramars Farahi, who I very much respected as a professor because of the quality of his work. Man was good. That could do the experiment. Well, they set up the experiment. They bought this really, at the time, it was very expensive. It was a 5-watt green argon laser. I remember, you look at that thing, my goodness. I looked at it against the wall. They told us not to look at it. I looked up at it against the wall, seeing the sparkle of it, and I saw green in my eyes for about 10 to 15 minutes. I kept seeing green spots, green sparkle spots. It was so intense. But it had a lot of energy transferred per unit time over a small area. They did the experiment. No result. The answer, 0 mass when they did the analysis. No mass. Not like Roberto Duran. No mas, no mas, for some of you boxing fans. But it has showed no mass based on the experiment. Well, the guy from Cornell was like, you did your experiment wrong. This is what you should have done. Farahi did the experiment. About the third time he did it, when I heard Farahi was getting a little upset, and every time they did the experiment, it came out no mass. So the guy basically said, Farahi didn't know what he was doing. He just wasn't very good at what he was doing. Well, that didn't go over so well. We all have our egos, right? And Faramars was an Iranian guy, very soft-spoken. I may have mentioned, he talk like this. He called theta, tita. And we'd have fun picking on him. Not to his face, of course, as you should. Not to his face. I know I do some goofy stuff too. But he did a presentation. I think, honestly, it was a setup. I think the department set up because they were trying to get rid of this guy because it seemed like they thought he was a sham. They were doing so the guy was talking about his work, and Farahi was there, and the grad students were there because we wanted to get this light has mass. Ooh, let's see that. And about 2/3 of the way through, Faramars chirped up and ran, you can't do that. The math said you cannot do that. It's not valid. And we were like, he was like, well, why do you say that? And he was like, because of blah, 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 blah. He said a bunch of stuff. And Faramars was actually a cosmologist before he switched to optics because you can't get money in cosmology. And so, he was like, you're wrong. And he was like, no, I'm not. I mean, I'm wrong because this is what it is. This is the way math works. And I see it in my head still. And then Faramars gets up and starts going up to the board. And this was 35 minutes into a 45-minute presentation, 45-minute presentation. And he takes over the presentation. He stops everything and starts arguing with this guy in front of the board. And he kept saying, no, you're wrong. So at about an hour into it, so after they've been arguing up there for 15 minutes, 20 minutes, a couple of us were like, I gotta go to the next class. We were like, I want to see this. Nerd fight, right? We stayed, a couple of us stayed a little while, a couple of us left. I stayed for a little while and I was like, I don't understand what they're fighting over. I didn't understand the mathematics at the time. We came out later on, a couple of us a few days later, asked Faramars. Well, I didn't because I didn't work with him that closely. And I was going to ask, like, what happened? He was like, he does not know what he's talking about. He just made it all up. And he said, he's just wrong. And he knows he's wrong. And he just won't admit it. And we were like, wow. He was like, I did everything he said. I did the experiment. Everything. If he was right, it should have worked, but it didn't. And we were like, okay. And that was pretty amazing. Light, as best we could tell back then, doesn't have mass. If it does, that experiment wasn't one to measure it. And this guy's prediction on the properties of light, if it does have mass, were wrong. The problem was this guy was a full professor. You know anything about professorships? Being a full professor, when they brought him in, they just gave him that level title. It took about 2 years for him to get enough against him to get rid of him, basically, because they realized he was just a scam. And his whole research was just a scam. And I think they pawned him off on some university over in England or something like that, or somewhere else. The politics of universities, right? Let's look at electromagnetic waves and matter. This is 9.3. We'll do a little bit on this. The first one's pretty easy. So electromagnetic waves in matter. Now, everything we've been doing so far have been involved with vacuum, in a vacuum. And so we did Maxwell's equations in a vacuum with no charge and no current. But what we got to now take into account is we have a material there. And let's assume a linear material. And when you assume a linear material, that basically just means epsilon and mu, permittivity of space and the permeability of space. They're not mu naughts. That mu naught and epsilon naught are in free space. That's in a vacuum. Now, these things that basically give us that proportionality constant. Remember, I keep constantly harping on this. These constants are just proportionality constants, relate the forces and the things causing them, which are just how much space allows it to be modified by these fields, or how much it lets the magnetic field travel through free space. That's permeability. Permittivity is how much electric field is actually permitted to alter space. So we're going to assume a material where those properties inside it are constant. They don't vary as you move through the material. Then Maxwell's equations, which define how electromagnetic waves move, how the E fields and the B fields operate in that material, we still got del dot E equals 0. We've still got del dot B equals 0. We've got del cross E. Now, well, it pretty much stays the same. Minus partial of B with respect to T. But here you've got del cross B